That's what my slide says. So actually, part 9 next week, part 2, part 3. So, and actually, I like the feel of that. So anyway, I think it's kind of nice to go kind of revisit some of those topics. So, and then if you're familiar with titrations is what we're going to do Thursdays, where you have this like glass tube, and you put liquid in glass tube, and you get a little stopcock, and kind of you get the liquid drip into the other liquid. So it's kind of fun. It's a method that's really common in analytical labs for various things, titrations. We'll get hands-on experience with that. And then that puts us at the following Thursday on the 20th. That is your unit exam. And you guys have like calendars and all that. So you guys know the 21st, which is not next Friday, but the Friday after. You guys don't have classes. None of your classes. The 21st. Yep. Now don't get your Fridays mixed up. Okay. So next Friday we're here, but the following Friday we're not. First 21st. Okay. I know. It just keeps getting better and better.
Isn't there a time change in this month?
First part of November, maybe. Here comes Mike. So don't be afraid. So I thought we'd take a running start at this and actually revisit this hydrated salt problem that we did kind of quickly at the end of, well, I guess it wasn't quickly, but on Wednesday. So remember, hydrated salt problems, you have to kind of somehow, I think, remove the effect of the waters of hydration, in which case there are 6 here. We did the first calculation. We actually went for molarity. I'm not going to revisit that. And then went for, which is moles of the anhydrous salt per liter of solution. And then we piggybacked on that and went to grams of salt per liter of solution. But one other thing I want to show you is, or related to this, is actually going for A first, which is grams of the anhydrous salt per liter of solution. So this is what it would look like. Basically, you could just flat out put the mass of the hydrated salt over the volume of the water, right? So we're getting closer. Somehow you need to tease out, that's the way I think of it, tease out the waters of hydration. And you can do that by this term right here. A few slides ago, actually, on Wednesday, we had that slide that had the molar masses of everything. So relative to the mass of the hydrated salt, okay, which has the waters of hydration, we have the anhydrous salt on top. Okay, so that's without water and that's with water. So that's the relative masses. So these will cancel out, and we're left with, actually, we're really close. What we have, grams of anhydrous per milliliter of solution. We want grams per liter of solution. Really common, we got to stick in one more term. To get liters instead of milliliters down there, we're going to introduce 1,000 milliliters over 1 liter, and that's it. That should do us. Unit-wise, we indeed have grams of NiCl2 over 1 liter of solution. And round to, wow, 4 significant figures. Okay, so you should get something like that. Which, remember, is commonly just simply called 18.14 g grams / L of NiCl2 in this case. So that's kind of how that goes. Any questions about that? So that's an alternate way. And you could piggyback on that grams per liter to moles per liter just simply using the molar mass then of the nickel 2 chloride. And that'd be pretty cool, pretty slick.
There's supposed to be an I right there with the 2 dots, right at the end.
Yeah.
Could be where?
Right after the end.
Yeah, this is Ni, yeah. That's my I.
It was like somebody assembled it.
Nickel 2 chloride. So it seems like the problems I collected, you didn't do the the C on the first one and the B on the second one. So let's take a quick look at those. Is anybody kind of waiting to do those? Because I said you could. Okay. So for what it's worth, now that my brain's not entirely boggled with 10 million different things going through it, let's see what we got. It kind of combines things we've talked about before. Okay, so it was C here, so I'm going to kind of fast forward to C. Okay. All right. So C says it gives you a density and it gives you the volume, and it gives you two volumes. So it looks like you're taking the 125 milliliters and you're dissolving it up with water to make your 15 liters. So it looks like I have a picture here. This is my dosing my water with my methanol. Okay, and there's the total volume after it's diluted. The density of methanol is given. So what's the question? What are the molarities? Okay. Cool. So can you see where we can actually use this volume and the density to get to grams of MEOH, by the way, is shorthand for methanol, methyl OH, hydroxyl group, MEOH. So we can use we can get to moles of methanol by taking this volume of methanol, this density of methanol to get grams, and then we have to use a periodic table to get the molar mass of methanol. So that would give you, then with that molar mass, that would give you moles. And you're really close. We're going to be talking more about this this is like a dilution problem. We'll be talking more about this. But you get the moles in what your 125 milliliters, and that's going to be diluted into 15.0 liters. So once you have moles, you're almost there. All you got to do is divide by your 15.0 liters of total solution. And that's it. So there's that one. And then B on the next, fast forward. Oh, was it C? Oh, I guess it was B. So B apparently is similar. We have density. Again, it's a dilution problem. We're going to be talking more about dilution problems. If you see two volumes, you ought to say, oh, I bet it's a dilution problem. So we have 35.0 milliliters. And we're going to dilute it up to 425 milliliters. So you're going to use that volume and that density, that milliliters and that grams per milliliters to get to grams. Then you're going to use molar mass to get from grams to moles. And then you're going to divide that moles by what? 425. So that's kind of how that one goes. All right. So let's see. Anytime you see like a physical property like density or a characteristic like molar mass, if you look at the units of that property, you know how you can use it in a factor label problem as what we call a conversion factor. So the two ways of describing solution concentration that we talked about Wednesday was this one, which is grams of solute per liter of solution. So what I mean to say is you can go back and forth between those two quantities. If you just look at the units, you know what you can use that concentration to go back and forth between. Okay, molarity is the same way. Molarity is always unpack molarity. I should never see a problem where you just leave molarity a big old M. That ain't gonna do it. Okay, what molarity means is moles of solute per liter of solution. And again, if you have, how do I say this? If you have moles of solute, you can go to liters of solution, and if you have liters of solution, you can go to moles of solute using molarity. Just let your units do the heavy lifting. And then we talked about weight percent back in the unit 1 in here. And weight percent unpacked is grams of solute per 100 grams of component over 100 grams of mixture. Well, this is grams of component of solute, and in this case your mixture is your solution. So grams of solute over 100 grams of solution. So that's our conversion factor. If we have grams of solute, we can go to grams of solution. If we have grams of solution, we can go to grams of solute. So that's kind of how that works. All right, so let's do some problems. Dun, dun, dun. So I see a G/L. You know, I'm going to have to unpack that as grams, in this case, of NaCl to 1 liter of solution. Now, sometimes I just look at the numbers and the units and say, well, what would you think that problem would do? Okay, so in this case, it says what volume of solution. So arrow, on the right of the arrow, I put volume solution. Okay, will contain 20, or, well, let's not do the words, just grams of NaCl. Sorry. Okay, so actually, this right here is going to do it for us. When you unpack 14.3 G/L, you end up with 14.3 grams of solute, which is grams of NaCl, over 1 liter of solution. And we talked about how we can actually, the inverse is great for the solution too, appropriate. For the same solution, we could say 1 liter solution over 14.3 grams of NaCl. Of course, these are the flips or the inverses of each other. And depending upon what we're given and what we want to get to, we're going to use one of these two ratios. So the first term, when I work these, the first term is always the thing that's not a property of the solution. That concentration is a property of the solution. What's not a property of the solution is the mass that we're after. 22.3 grams NaCl. I usually put it over 1. So I not want grams of NaCl to cancel. So I'm going to use what? What I call the flipped version of the concentration grams per liter. So if my second term is the concentration of NaCl, 1 liter of solution over 14.3 grams NaCl, then I'm liking it. My units of grams of NaCl cancel, I'm left with liters of solution. Sometimes be careful with volumes. Every once in a while it says how many milliliters, and then you're like, oh, drat, you have one more low conversion. So round it to 3 significant figures. Is this what you got, Mike?
Yep.
You're so going to open that window. I'm hot.
It's kind of warm.
Is it warm? Get droopy. Does that work? Okay. Well, I wish they were all that straightforward, but you know they aren't going to be. So we're just kind of going through some, and if this gets too cold, then you just close it, okay? Let's do another one. Remember I said you should never work a problem with M in it, okay? So you see that 0.255 M? See, when I read story problems, sometimes they just freak me out. So I just go straight for the number and the units. So I'm going to use that, and on the next slide I'm going to unpack that. So let's do it this way. This is probably going to be my first term, 0.015 moles. Okay, and I know since I looked at it in my office before I came, it's a 1-stepper. Actually, I guess it's a 2-stepper. But I ultimately want to get to question mark milliliters. Question mark milliliters. Well, the big M, like we talked about a minute ago, big M's are always, what, moles, in this case, of K2Cr2O7 potassium dichromate per 1 liter of solution. So if that's the case, wow, I can go from moles to liters with molarity, and that's exactly what I'm going to do. So I'll put molarity right there. And that will leave me with liters. And this is one of those cases where I said, be careful if you want all your points, blah, blah, blah. We're going to have to do one last tack-on little conversion to go from liters to milliliters. We can do that, the factor of 1,000. I can never remember if you multiply or divide, so I just set it up and see where it goes. Okay, so yeah, like I said, make sure you unpack those M's Now, if you're only dealing with one solute, K2CR2O7 in this case, you don't have to label what the solute is. So the first one could be 0.255 moles over 1 liter, and the other one would be 1 liter over 0.225 moles. But one of those is going to be our second term to get down the road. Oh, that feels a little better, doesn't it? I think so. Okay, so the first term's not going to be molarity. That's how I usually do it anyway. The first term is going to be anything but that. It's 0.015 moles, K2CR2O7 over 1. And I want moles to cancel, be left with units of liters, which I need to get to milliliters here in a minute. But then so to do that, I'll use what I call the flipped version of the molarity. 1 liter solution over 0.255 moles. So our moles cancel, we're left with liters. So what do you think for that last term? How are we going to get to milliliters?
1,000 milliliters over 1 liter.
Yeah, I'm liking it too. 1,000 milliliters over 1 liter. That'll get us all the way. So now everything cancels except for, I love canceling things. Cancel, 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 remain. So how many significant figures, guys?
It's like 2.
I'm thinking just 2. Yep, because that one doesn't count. But these 2 do. And in this we have 3 sig figs. But we go with the fewest. So 2 sig figs, I got 59 milliliters. Double check that. We have confirmation. Any questions about that? So that would be what we call a moles, that would be a moles to volume problem. Okay? All right. Well, this looks like a volume to moles problem. Again, just kind of look at the numbers and what the units are. We have our molarity. We're going to have to unpack that on the next slide, or I think I unpack it right here. 0.108 m means, in this case, 0.108 moles CaCl2 per or over 1 liter of solution. So I think I've got my strategy on the next slide. So strategy kind of looks like this. Our first term is going to be our milliliters of solution. And we're going to have to go ahead and get it to liters of solution first. We can do that. And the reason it needs to be in liters in solution, because molarity is moles per liter. And then once we have liters of solution, we can go ahead and use molarity to get to moles. Not too bad. So the first term is not going to be molarity. It's going to be our volume, 75.0 milliliters. So this is where if we get it, I say we, if we get in a hurry, we might just put down 75 milliliters. And if we do that, then we will lose a point on the test. Okay, because you,
If we put just what?
if you don't put that 0 there,
Oh, okay.
0.0, unless you catch it in the end. Like if you go ahead and just say you put 75, but you round it to 3 significant figures if you're allowed 3, okay, then you're fine. But usually if I do that, then I'm like, oh, that's 2 sig figs. All right. So I usually put that over 1. Now we're going to go to liters. So, of course, that looks like 1 liter over 1,000 milliliters. Then we're going to stick in, use the molarity to get to moles. What does that look like?
Moles over liters.
Yep, we moles over liters. So we have that 0.108 moles over 1 liter. So unit-wise, that's all looking pretty good. Milliliters cancel, liters cancel, and we're left with units of moles, which is perfect. How many sig figs?
3.
3. Did you get this? Ah, this is a good one to round to 3, right? So these two leading zeros after the decimal don't count with regard to being significant. But this last 0 right here counts because it is a trailing 0 after the decimal. So that's 3. All right. That's not too bad either. So those are kind of the pieces, new pieces. Well, this is taking it up just a little bit. Okay? So if you read it a few times, well, you can, however you want to do it. So what mass of glucose, so over here, question mark grams, okay, is 125 milliliters solution. Okay, now notice molarity is given, and we need to unpack molarity. Can't remember if I unpacked it on my next slide or not. But that will get us what? From moles to liters or liters to moles. In this case, it would be awesome if it got us from liters to moles. Do you guys buy that? We can go from milliliters to liters, and then we can go from liters to moles using molarity. And then how can we get from moles to grams? Molar mass. Molar mass, the periodic table. Oh, pretty good. Now, sometimes students like to kind of break it up, and you definitely can do that too, but I'm going to kind of string them up together. All right. So is this where, oh, this is the, I have a few of these slides. Maybe recently we've calculated the molar mass of C6H12O6, but you're going to see it magically appear here. So don't do as I do, do as I say. So you need to show that, but I'm going to kind of show it to you in context. So the first term is going to be the volume in milliliters, that 125 milliliters solution over 1. And then we need to get to liters, so it looks like what? 1 liter over 1,000 milliliters. And then we're ready to use the molarity term. We want to be left with moles, so we're going to leave moles on top, put liters in the bottom. So that looks like that, 0.432 moles. And again, if I was taking notes or doing this maybe even on a test at this point, since I only have one analyte, I probably wouldn't write C6H12O6 all the time because I would get frustrated. So the molarity, 0.432 mole over 1 liter. Then we have to, or you're looking to see the molar mass. And here's the thing that's magically appearing. So we want moles to cancel, okay, be left with grams, so we use what I call the unflipped version of the molar mass. So somewhere in your notes, we calculated the molar mass is 180.16 grams over 1 mole. Okay, so then our moles cancel, we're left with units of grams, which is perfect. That deserves chocolate. Any questions about that? Unfortunately, the more complicated they get, well, unfortunately for me, there's multiple ways of getting to the right answer. I'll just kind of follow as long as you show all of your work. But unfortunately for you, it's kind of hard to see how to get there. So 3 sig figs, I got 9.73 grams. 9.73 grams. Okay. Any questions about that one? No? Well, hearing none, we'll just go on. All right. Another problem. The more you do, I'm a firm believer in the more you do it, whether it's in class or at homework or for lab, you know, the more it's hopefully going to sink in and you can do it on the test. So I see 2 numbers I need to unpack. Okay, I see a percent acetic acid and I see a density of the solution. A lot of times, let's see, acetic acid vinegar. That's vinegar, actually. You know, you pick up a jug of vinegar, you're like, oh, well, that must be pure. Actually, it's just a dilute solution of acetic acid. It's like mostly water. Okay. So this is one where I'm gonna unpack those two, and I'm gonna play around with it ultimately to get to molarity. So this isn't where I have a first term and I work through it. Okay, but what I usually do, and I'm going to unpack the others here in a minute, but what I usually do is somewhere in there, what is molarity? So I put a question mark, moles, and I usually do like AA for acetic acid, moles of acetic acid per 1 liter of solution. That's my goal. If I can get those units, moles of acetic acid over liter solution, I am done. So, of course, unpacking the weight percent and the density looks like this. Okay, weight percent. What does 76.0% acetic acid or AA mean? It means that in 100 grams of the solution, the jug of stuff, okay, you will have 76.0 grams of pure acetic acid. Well, that's cool. Well, this is where students, or I should say myself sometimes too, we kind of, with density, does this make sense? That the density isn't the density of the solute. The density is the density of the solution. So here's where I'll use the word explicit. We need to explicitly say grams of what? That's grams of solution. Why? Because if you look up above that, we have 2 grams. We have grams of solution and grams of solute. In this case, acetic acid. So you have to be explicit or it's not going to work. So density is 1.07 grams of solution over 1 milliliter solution. That's it. So those are our 2 puzzle pieces. And like I said, we're after moles of acetic acid per liter of solution. So here we go. Well, you could probably kind of see with those 2 terms maybe how I can maneuver them to get to grams of acetic acid per milliliter of solution. And then, of course, I can change the milliliters to liters. That's fine. But at some point, I'm going to have to get from grams of acetic acid to moles of acetic acid. And how do we go from grams to moles? You would tell me the molar mass. So here's one more thing you need to kind of work out in the margins. And I did go ahead and use a periodic table to show you the molar mass of acetic acid, 60.05 grams per 1 mole. What you guys got. Cool. Okay. So here we go. We have 3 puzzle pieces. Now we have 3 puzzle pieces. And with the whole liter, milliliter thing, that would be a 4th puzzle piece we can get down the road and make it work for us. There's definitely more than one way to skin a cat. We talked about skinning cats, didn't we, the other day? Okay. All right. So if we start out with this, we're a few steps from moles of, and if you want to put AA instead of CH3COOH, you can. That's my AA, moles of AA. We're a few steps from getting moles of AA to liter of solution. Can't remember what I fixed first. So notice and you don't have to put it in this order, but the first thing I'm going for is to changing the grams of AA, acetic acid, to moles. And you recognize the second term is the molar mass. So if I put 1 mole or 1 mole of AA over 60.05 grams of AA, my grams of AA cancel. And we're left with moles of AA per 100 grams of solution. Right? Well, we need to do something with that denominator because it's units of grams of solution. We've got to fix that. So notice the next thing I did to get grams of solution to cancel, okay, is to introduce the density. So that 3rd term up there is the density. This is rho. This is the density. And the reason I did that is now grams of solution cancel, and I'm left with, in the bottom, milliliters of solution. And we said earlier that grams of acetic acid cancel, and we had moles. So now we have moles per milliliter. Almost there. This is kind of cleaning it up. We want in the denominator units of liters, so it looks like 1,000 milliliters over 1 liter. We'll finish it up. Any questions about that? So unit-wise, we are indeed just simply left with units of moles per liter, which is perfect. So I focused just on the units. And 3 significant figures. So I got 13.5, and here I would pack it back up with a big M. I would just go 13.5 M molar AA, or acetic acid, CH3COH, CH3CHO. So that was an example of using, a weight percent and a density to knock out for that solution what is its molarity. All right, so let's take a look at these 4. 35, 36. There you are. All right. How much glucose in grams must be dissolved in water to produce 75.0 milliliters of a 0.350 molar glucose solution? So here's my hint for A. This is what I would do. It's kind of almost reverse engineering. This is the volume of solution you want. Okay, 75.0 milliliters. Of course, I want to use molarity here in a minute, so I got to go to liters, no problem. Reverse engineering. And then I can use molarity to get to moles. And then once I have moles, MM of course stands for the molar mass. Once I have moles, I can go to grams using the molar mass. So basically you're saying what grams would you have to dissolve a total solution volume of 75.0 milliliters to get that molarity in question. Let's look at the second one. Oh, it's got density in it. That can't be good. So density, we're dealing with methanol. Density is given. And it asks not how many grams, but how many milliliters would you need to go ahead and dissolve up. You're going to take a certain volume of methanol and you're going to dissolve it up into 2.25 liters. And when the dust finally settles, you want that given molarity. Okay, so again, if you just I think of it as kind of starting at the finish and going backwards. Well, our target volume of your final solution is 2.25 liters. Okay, how many moles must be floating around in that bucket of 2.25 liters? Well, we can use the molarity to get to moles. Once we have moles, we can use the molar mass to get to grams. Once we have grams, we can use the density to get to milliliters. So it's very similar to A, except it tacks on density. So, if you're like a lab tech, you just they tell you what they want and you go and prepare it. So, and keep records of how you prepared it and hopefully you prepared it correctly. All right, so how much ethanol in liters must be dissolved to produce, your target is a total volume of 200 liters. That's a lot of liquid. 200 liters with 4 significant figures with that given molarity. And I think this is kind of similar to one we looked at. We can use our final volume of solution, the final molarity of the solution to get the moles that must be running around in that 200 liters of gunk. Once we have moles, we can use the molar mass to get to grams. Once we have grams, we can use the density to get to milliliters, and of course, one last step. What's the liters? And B must be similar. Oh, it adds something. It adds a weight percent. Every once in a while in General Chemistry 1 and General Chemistry 2, I will give you a number that you don't need to use. That is so cool. I don't do it very often, but it's just almost kind of a natural sort of thing. But you need to use this weight percent, all 4 of those numbers. There's 4 numbers there. But if we kind of do it a similar idea of what we did before, okay, our final volume of solution we're after is 12.0 liters. The molarity's given so we can see how many moles must be swimming around. I almost like pictures of those moles swimming around. I know they don't really move by themselves. Well, actually they do, Brownian motion and all that. So moles, okay, we can get to the grams that must be running around using the molar mass of HCl. Okay, so that's grams of pure HCl. Then we have to say, oh, drat, the stuff we're using is not pure HCl. The stuff we're using for every 100 grams, for every 100 grams that we dose it with, only 36.0 grams is pure. Okay. So we're going to use that. To me, I'm going to flip that term. That makes sense to you. That's actually going to be the flip term right there. Grams of HCl will cancel. We're left with units of grams of the solution or concentrated HCl on top. Then we just need to use the density to get to milliliters. That's that. Dang, there's more? I can see on my, my thing here. I'm only on, that was page 2 of 5. All right. Looks like we're probably just going to stop with this assignment slide and pick it up on Monday. But let's finish looking at these, okay? Which has a higher concentration? Oh, I remember these. Okay, so we have 2 solutions. It's kind of fun. Kind of like a little detective story there. One solution, its concentration is given in weight percent. Another concentration, the other solution, its concentration is given in molarity. Okay? So what I would do, and there's lots of different ways to work this, so sometimes you just want to set aside, just ignore my hints or whatever, that's fine. But what I would do is take that weight percent, because you're given density, you should be able to use weight percent and density like we did before to get to molarity of A. So I would convert those. I would convert A into molarity, and I could compare it directly with molarity of B. That's what I would do. Yeah, blah, blah, blah. Okay. I think you got the idea. We kind of did one of those. The next one I think is similar. 4 out of 5. Oh my goodness. This one's very similar. If you look, there actually are 2 solutions. We have white wine with a weight percent of ethanol, 11%. And then you need to go back, and I went ahead and see this purple, this blue box right here in my hints? That actually is an excerpt that is associated with example 4.8. Sometimes you're like, 4.8? I have no idea. Well, that's what 4.8 will tell you. So basically, you're comparing 11% to that 1.71%. Again, since you're given the density and the weight percent, you can use those 2 things to knock out molarity of your white wine and compare it with that solution. That's what I would do. Oh, see, there was no 5. It's like, whoa. Okay. So if you're okay with that, I think that's a good place to stop. We do need to tackle a little bit with part 8 still. We need to finish dilutions and electrolytes on Monday. And then kind of start titration chemistry, part 9. Okay?
I have a quick question on the 42.
Back.
What is the example 4A? What is the...
I can't remember. But what I did want to make sure students have is this is, if you go to 4.8, this is the answer to 4.8.
Okay.
It's like ultimately, what's the molarity of the ethanol in the solution, and that's the answer. Yeah, but I can't remember the details of it. Yay. You're welcome.